Today, we are going to be addressing the following question. Prove that the transformation resulting from multiplying a vector in Rm by an n by m matrix is linear. Hello, welcome back to the Quant Plus YouTube channel. Proofs are an important part of mathematics, and for many students in mathematics and related subjects, the first time seeing rigorous proofs can be a challenge and can be a wall that they have to get around or get over. Many courses can serve as an introduction to proofs, but today I'm going to be discussing an example from linear algebra. So, the first step is to kind of think about it a little bit, maybe a little bit less formally, and try and translate our ideas. If A is an n by m matrix, then we can think about it as being a matrix of this form. Where we have n rows and m columns, and accordingly each spot in our matrix is filled with some value. Accordingly, V is going to be defined in this way, where V is some matrix in Rm, therefore it has m entries, or m components. Well, what does it mean to be linear? If a transformation or a function is linear, then it preserves scalar multiplication, and it preserves addition, right? And by extension, you can think about subtraction as adding a negative number, and you can think about division as dividing or multiplying by a fraction, and so we also get division and subtraction. How we can write that out formally is that if the transformation t of some vector is linear, then t times some constant, or t time the transformation of some vector v1 plus some constant, which I'll label c, times some vector v2 should be split apart, right? Or if this transformation is linear, it will be preserved as following. So if we can demonstrate that multiplication of this matrix A by this vector v preserves this kind of a relationship, then we've gotten what we want, and we can break it up into two separate pieces. Well, as a reminder, the standard way of multiplying can be described as following. It's the first row of A dot V, right? Where this is the dot product. And similarly, you keep going down until you get to the nth row of A dot product with our vector V. Well, to make our lives simpler, right, we can pick an arbitrary entry or component in the product, and as long as this relationship is preserved for an arbitrary, let's just say jth entry, well, then that result can be extended, and this results in a general proof. Well, let's see. If we break this apart into two separate pieces, addition first and subtraction second, then let's think about it in this way. For the addition part, let's define two vectors. We have our v from before, which I'm writing as a column vector. And we're going to define a new vector in Rm, which we're going to label w. And to make this more formal in the language of proofs, then let's write it this way. Let v be defined as this, and w, which we define as this, be two vectors in Rm. Then v plus w is equivalent to v1 plus w1 all the way down to vm plus wm, right? Because we know that the addition of vectors is done component-wise. So then subsequently, I guess we can say, the transformation of v plus w is equivalent to multiplying the vector v plus w by the matrix A. The jth component of A times v plus w is defined as the jth column of A multiplied by v plus w, where multiplication implies the dot product. From here, we can write this as A of, we can write this, we can then split this apart, right? Because we know the dot product of two vectors preserves multiplication, preserves addition. So the jth component of A of v plus w equals the jth component of AV plus the jth component of AW. Because J is arbitrary, this relation can be generalized showing that A of v plus w is AV plus AW, and that this transformation preserves addition. if we then do the same thing for scalar multiplication, then we'll get our result. So for scalar multiplication, let k be an arbitrary real number. Then k times some vector v is equivalent to k times v1 all the way down up to k times vm. Right? Because the scalar multiplication of a vector is similarly done component-wise. Therefore, a times some kv, again, we're going to use the jth component argument, so therefore, the jth component of a times kv is the jth column of a dot product with k times our vector k times v. The dot product preserves scalar multiplication. And inherently in writing this, I'm assuming that we've already proved that the dot product preserves scalar multiplication, and before that this dot product preserves addition. But I'll leave that as an exercise, as they say. So the jth component of a times kv is k times the jth component of AV, demonstrating that scalar multiplication is preserved. And then as a final step, by combining our previous results, we can conclude that the transformation is linear. And that is exactly what we want to prove. So, in summary, the main idea with proofs is that you can't just jump to things, right? Every step that you make has to build upon the previous step, and every step that you make has to be justified by some previous finding. If you found this content informative, please support the channel by liking this video, sharing it with your friends and family, and subscribing to the channel. Additionally, if you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.